just to remind you, you've been dealing with geological maps in the last few weeks. The last lab that we had where we dealt with geological maps, you should remember one that looked like this. This is the map of the Grand Canyon. And one thing that I want you guys to understand that's similar with our area as far as the Grand Canyon is that there are beds within the Grand Canyon that are horizontal. And remember when we looked at the Grand Canyon, we made you focus on these green layers, which is the T-peat sandstone, the Bright Angel shale, and the Muave limestone. And we asked you guys a question, can you tell the attitude of those beds? And in this case, you should have been able to say, yes, when I look at those colors and their outcrop pattern, and if I notice the contour lines, you can see that the contour lines are roughly parallel to the contacts between the formations. So that indicates to us that those formations within the Grand Canyon were horizontal. The case is different for the layers that are exposed down at the base of the Grand Canyon, and we tried to explain to you so that you could see exactly why we would indicate that some of the layers were perfectly vertical and some of them were dipping. Now, if we refer back to our map of the Washington County, Ohio, again, if we look in the areas that are over here on the map, remember Marietta's over in this portion, and then the place where we're going to the northern end of the Burning Springs Anticline is over in this location. But if you look in the area around that where you can actually see the outcrop, these turquoises and the purples, those colors are roughly in patches that are kind of dendritic. If you remember the word dendritic, when we used that word before, we were talking about drainage patterns for streams. And there are streams, and the streams are following dendritic patterns. But in this case, the blue, darker turquoise or darker baby blue patches that are making the tops of the hills are also giving you sort of that irregular fractal pattern that kind of looks like a dendritic branching pattern. And if you look between them, in the valleys where you can actually see the rivers, they're following dendritic patterns as well. Well, the key thing is here, similar to the map of the Grand Canyon, the contacts between the darker baby blue and the darker turquoise in these areas, that dark line on that map is parallel to the contour lines that tell us that these beds are roughly horizontal. So again, in this area, the darker purple blue, which is the Dunkard group, are the hilltops in the area, and in the valleys, in the river valleys, this sort of turquoise color is in general the Monongahela group, which is the older Pennsylvanian age layer. And they're horizontal. Now I'm going to pose to you this question. We're going to travel from here in Marietta upriver about 15 to 20 miles to this area where we can actually see the light blue cropping out. The light blue stuff is coming to the surface, and that's that Conemaugh group. Now, if we were to measure the thickness of the rocks between where we are in Marietta, which is roughly at the contact between the Permian and the Pennsylvanian rocks, between the Dunkard and the Monongahela group, and then if we measured how many feet down it would be to the Ames Limestone, it would come out to about 500 to 800 feet. So my question is this. If we were to drive up here, the elevation of the Ohio River and basically where we are is about the same here as it is in that area right around Newport, Ohio. If the layers are perfectly horizontal, how can it be that if we go to that place upriver, there's suddenly older rocks that would normally be 500 feet down? And the answer is not that there's a big hole there. If there was a big hole there, of course it would be filled with water and it would be a giant lake. That's not the case. They're at about the same elevation. So the Ames Limestone there is at about the same elevation as some of the much younger rocks here in Marietta. And many of you already have the answer to that, and that is yes, indeed. There's something structural going on in this location. So although I said in general the beds are horizontal in this area, at this location, that is the northernmost exposure of a structure that we refer to as the Burning Springs Anticline. And that is an anticline that extends from down south in West Virginia up here to right around Newport, Ohio. It's kind of an important feature because it's been an active oil and gas producing structure for more than 150, 160 years. And it still is producing today. On this map, if we zoom in, you can see a few of the structural contour lines that are based on one of the formations that's down deeper within the strata. But this is brought to the surface, and then the surface is eroded fairly evenly. So although we still have hills, where the higher hills are basically capped by sandstones, and the valleys are places where a lot of those sandstones are missing, the overall elevation of the hilltops in this area are no higher than they are over here in Marietta. Now, if we move over here to our stratigraphy, I want to refer for a few minutes to our Paleo Geographic Map and to the stratigraphic column that is in your lab that we are giving to you. First, let's look at the Paleo Geographic Map. This is a Paleo Geographic Map of all of North America during the Pennsylvanian period. So that's about the time that the Monongahela and the Conemaugh formations or groups were deposited. Going across that map is the paleoequator. So what's interesting is to realize that North America at that time was tropical. So the plants that are growing on the surface, many of them were in tropical rainforests, different from today's tropical rainforest because the main organisms were seedless vascular plants and some primitive gymnosperms. Nonetheless, in this map, again, if you focus on this darker area right here, that would be the Appalachian mobile belt. And at this point, we were experiencing the Alleghanian orogeny, which we'll learn more about in class. At the time, the areas to the west of the Alleghanian Mountains were what we refer to as a Foreland Basin. And a Foreland Basin forms when a mountain range pops up on the edge of the continent, and just like you standing on the edge of a diving board being a weight, that mountain range pushes down on the continent and the edge of the continent sags down a little bit, creating a space for the sediments to be deposited. So during the Alleghanian orogeny, sediments were deposited within the Appalachian Basin, which is a Foreland Basin. Nowadays it trends northeast to southwest along the edge of the Appalachian Mountains. Keep in mind the Appalachian Mountains of the time that we look at today were just the foothills of the big mountain range, and the big mountains would have been over where Washington, D.C. is, and Richmond, Virginia. So we are sort of in the coastal plain, you might say, of that mountain range between the ocean, which would have been to the west and to the northwest of us. And so between the mountains and the sea is basically the area where Marietta was. Now, we were very close to sea level on that coastal plain, so when sea level went up, we had transgression, and that just a little bit of sea level rise could have caused the shoreline to migrate inland quite a ways. And just a little bit of sea level lowering could have caused the shoreline to migrate back to the west, thus giving us a regression. So transgressions and regressions occurred across this coastal plain. Now, on this map, Marietta, Ohio is right in here, just south of, we did include some of the features that are modern day features on there. So you can sort of see where the Great Lakes are today. They were not there during the Pennsylvanian period, but Marietta would have been just south of the one that would be Lake Erie much later. And we were on that flat coastal plain. Lazy rivers were carrying sediments from the mountain to the sea, and that would have been from the east towards the west. And we can actually track some of those river valleys today. We can look at the river sandstones and see how they tracked through the shales and the coals, especially during low stands of sea level when this area was a broad coastal plain that was above sea level. Now, when the sea level went up, the transgression occurred, and the sediments that would have been deposited around here were mainly shales. And then at the highest, the sea level pushed shoreline so far to the south of us that we resulted in having a very clear, warm, tropical, shallow ocean on the surface of the continent called an Epiric Sea. And we had the conditions that were conducive to the deposition of limestone. So we have some layers of limestone and shale deposited when sea level's higher. Now, in this diagram, you can refer to the one that we're going to give you. You might not be able to see it real clearly, but this is the diagram that shows us the thickness of these units. At the very bottom is the Conemaugh group, and that's the group that we're going to go and look at near Newport, Ohio. On top of that is the Monongahela group, which is the group that makes up the valleys in the outcrops around here. And then on top of that is the Dunkard group, which makes up the hilltops around here. So stratigraphically above one another, and we can actually go out and see them. And in places such as in the Burning Springs Anticline over there, we can actually see where the Conemaugh has been brought up to the surface. Now this level that we're at is right about where my finger is, and if you look at the thicknesses of the rock units about the boundary between the Conemaugh and the Dunkard group, and then go all the way down to near the bottom where it says the Ames Limestone, that's the thickness of the rocks that would have been between where I'm standing now and the outcrop of the Ames Limestone. Well, it's right below me right now. I'm in Marietta for the time, but we're going to go to the field. So that maybe 600 or so feet of rock has been eroded away at the location of the Burning Springs Anticline, and thus we have these rocks exposed at the surface. Now, before we go any further, I want you guys to refer to these two stratigraphic sections. They're hand-drawn by someone that's very talented at drawing a nicely hand-drawn measured section. Okay, I did draw them. I want you guys to understand that this is the outcrop from the location that we're going to go to. And they're both showing that same location, but the complete section, columnar section A or measured section A, is at a smaller scale. So the part that we're actually going to go and stand next to in the field is just this lower part. But measured section B is a zoomed in section where we've expanded that lower section so you'll have space to write and make observations and take notes while we're out in the field. So this is the same as that. Now we've numbered the layers from layer 1, 2, 3, 4, 5, 6, 7, and 8. And then you can see on the larger, more complete section, we go all the way up to number 12, which is sort of at the top of the outcrop. So we're going to go and describe those. Don't write anything in these sections until we tell you to just yet. And we're going to explain to you why those interpretations are going to be the interpretations that you're going to place in those areas. Now down here are 3 other pages that are included in your handout, and those are some of the fossils that we're going to encounter. One page has fossils that are marine fossils, shelly fossils, similar to things that you guys have already identified in your labs. What does that indicate about some of the layers? Well, it indicates that some of the layers were marine, and they were an environment that was conducive to the growth and life of those types of organisms. These other 2 pages show fossils of organisms that are plants. And these are some of the organisms that lived in those coal swamps that made up the coal from the Pennsylvanian period, or the late Carboniferous. So we will actually see some of those, and you'll be able to use some of these genus names. The location that we're going to take you guys to, those fossils are actually quite beautiful, and you could actually sell some on eBay for big bucks if you go back out there. Maybe we'll keep it a secret about where exactly we're going. All right, and before we go out, I just want you guys to pay close attention that these are graphs. Remember, we talked about them in class, and what they're actually showing us is the grain size going from finer to coarser and the actual thicknesses of the units. So we've done some of the job for you already, and we've actually done some of the measuring. Keep in mind that there's a lot of information, just like there's a lot of information on those topographic and geological maps. We're including types of rocks, we're including types of fossils that are present, and other sedimentary structures. And as you look at the diagram, make sure you notice that there are patterns as well. And that's one of the things that we're always looking for, associations of different facies or different rock types that show us patterns. One of the main patterns that we're going to focus on these diagrams is the fact that there are wiggles that are going back and forth, meaning the sediment's getting coarser and finer and coarser and finer. And then going from the bottom of this unit, remember the oldest is on the bottom, youngest is on the top, going upward from the bottom of layers, say 6, 7, and 8, all the way up to the top of it, you'll notice that there's a gradual coarsening of the sediments. That coarsening tells us something, and it will have something to do with sea level change and one of your favorite words, progradation, especially of deltaic sediments. So the next time I see you, we'll be magically at the outcrop, and we'll be showing you some of these features. All right, here we are for our second small installment, and we have some cars driving by, so I'll try to stop driving when they're driving, or stop talking when they're driving by, but we're at the outcrop. It's right behind me. It's a little overgrown, and I'm hoping that sometime soon the Ohio Department of Transportation will improve this outcrop, because as we drove up, we did notice a few brand new landslides. One there and one about a mile down. So hopefully they'll see the need to help us dig out this outcrop. But what we're going to be looking at is behind me. We're not starting from the very bottom because a lot of the interval is covered, but from about 20 feet from the road, 20 feet up, there's a little area that we're going to go stand on, and the bottom of that area is the bottom of our measured section. That's the zoomed out measured section. And so from back here, what I want you guys to notice, well, I don't know if you can see it at all, but the bottom of where your handout says layer 1 is at that spot. There's a little flat area about 20 feet up, like I said. That's where we're going to go stand. And then the very top of the outcrop, way up there, you can see some telephone lines. That's the top of your measured section. So where we're going to go stand, we're going to be able to see layers 1 through maybe the base of layer 7. We are not going to climb up unless I feel like sending Dr. Godum or Dr. Smith up there to collect samples. But normally when you guys are here too, I don't force you guys to go up there as well. What I want to do right now is, while we're talking, before we go up to the top of the hill, I want to review what I said about the paleogeography, if I can find my Paleo Geographic Map real quickly. What you guys need to understand about these sediments is that they are Permian in age, and they are from the the Pennsylvanian period. Remember, the rocks that were on the tops of the hills in Marietta were Permian. These are Pennsylvanian, and these are part of the Conemaugh group. So if we can zoom in and show the measured section again, we're actually going to see that some of the names of the formations are on your handout. The Conemaugh group is the big name for all the formations that all the formations belong to. And then within there are a whole bunch of different units. The one we're going to go look at is called the Ames Limestone, and then there's a coal underneath that. The one listed here is the Harlem Coal. The Harlem Coal is actually below us. The coal that we're going to see directly below the Ames Limestone on the outcrop is actually called the Ames Coal too. So we're going to see those units when we go up. I do want you to pay attention to the Paleogeographic Map. We're going to be looking at sediments deposited during the Pennsylvanian period. At that time, way to the east of us, Gondwana was smashing into Laurentia. Remember, Gondwana is the name for Africa and South America. Laurentia is the name for North America. At that time, the Appalachian Mountains formed. What we call the Appalachian Mountains today are actually just the foothills, the crumpled foothills of sedimentary rock that were next to the big mountains. The big mountains would have been where Washington, D.C. is, Richmond, Virginia, and some of those cities a little farther west. The mountains are all gone. They've been all eroded away. The mountains that are the Appalachian Mountains, the foothills, and the mountains that eroded away behind them, their sediments shed this way into the basin. So sediments would have been coming from the mountains to the sea, which would have been to my right, your left, would have been towards the northwest right now, and that's the direction of where the ocean was. This area would have been a coastal plain real close to sea level. And as sea levels went up and down, shoreline would have transgressed and regressed across this area. When the shoreline was regressed and was far to the north, this area would have been land, and you would have had swampy environments with lazy rivers carrying the sediments from the mountain to the sea. Now keep in mind, one thing I want to stress is when we bring people out and start talking about river environments, they think, oh, did that sandstone up at the top of the hill, was that deposited by the Ohio River? Ooh, no. The sediments here were deposited long before the Ohio River Valley, the Ohio River, was ever thought of, conceived, existed, whatever. These rivers that came out of the mountains towards the sea were entirely different drainage patterns. Keep in mind, there would have been thousands of meters, maybe thousands of meters of sediment deposited on this, and the Ohio River is basically dissecting down through those, exposing the older and older rocks through time. So we're down to now the Pennsylvanian rocks that are exposed here in the northern end of the Burning Springs anticline. And the sediments, the river channel sediments and the marine sandstone and limestone sediments are not related to the Ohio River. They are part of a separate system. So on the Paleo Geographic Map again, I want to point my finger to where we are, which is right about here. This black patch, pardon me, this black patch is the Appalachian Mountains. And you can see over to our west would have been where the ocean was, and we were on the low coastal plain next to that. So the shoreline would have gone back and forth depending on what was happening to sea level. Keep in mind, at the South Pole, Gondwana was a vast continent that had glaciers. Well, I should start by saying a vast continent that had part of it across the South Pole at the time. And because of global cooling and global warming at that time, we were going in and out of glacial cycles. Glaciers built up on the South Pole, sea levels went down and the ocean regressed. When the glaciers melted on the South Pole, the sea level rose. And because, didn't I tell you guys before we'd get people honking at us? And because we were near sea level at the time, the sea levels rose, the sea levels fall. We were in the area that got intermittent flooding and then draining and flooding and draining of the seas. All right, now let's go up to the outcrop and we will see the rocks up close. All right, so bear with us. It's been raining for the last few days and our outcrop had a little bit of a landslide fall down on it, so we uncovered a little bit of it. Now, once we're done here, we're going to go through the layers, and you should have your sheet of paper that looks kind of like this. And you should be taking notes in the adjacent layers, layer by layer, so that you can have information to write for your essay. So what we're going to do is we're going to go all the way down to the bottom and start looking at the layers one by one, and we'll talk about what rock types they are, and we'll also talk a little bit about some of the environments of deposition as we go too. So way down at the bottom is an area, layer 1, that is filled in with a little dash pattern. Notice how the line that's separating that up for the graph is very far to the left. That means it's very fine sediment. Now, when I tell you the description of these layers, I'm going to try to make sure I do it in a systematic, consistent way in which I give you the color, the sediment size, the rock type, and then any other features that we see, such as if we see concretions or fossils or bedding or cross bedding like that. So that's sort of a standard way to do it. But we're going to start way at the bottom, and what we find down here, if I have my hammer and I can get in there, unfortunately, like I said, we have to dig down to the layer because it got covered up with some of the layers. We can pull out some of these shale pieces, and the shale pieces have things on them. Now, the first thing that you might notice when we pick some of them up is that they're covered with a lot of orange stuff. We want to ignore that orange stuff at first because that actually came last, believe it or not. What we want to talk about mainly is the gray material, which is the original rock. And of course, as you guys have probably figured out, this first layer is very shaly. Now, one thing that we do when we're on the outcrop generally is a geologist will take the rock and, he just ate the rock. Well, I didn't really eat the rock. What I did was I rubbed a little fresh rock. I like to make sure it's fresh, so I'm sure that some deer hasn't peed on it or something like that. But I'm rubbing it against my teeth to see how silty it is. Clay is very smooth and pasty. But if there's a little bit of silt in the rock, then actually I can feel it. It's basically a little quartz there. I wouldn't eat a lot of that to make my teeth scratched up, but just a little bit tells me something about this rock. Now, the rock itself, when you look at it, is that gray stuff. And the little bit of grittiness on my teeth tells me that it's a slightly silty clay stone. Okay? We'll remember that in a minute. It's a color to the rock is medium gray. On the rock are all these little black pieces. And I actually lucked out right away and I got a beautiful fossil right there. I don't know if you can zoom in and see that one, but that's actually a fern fossil. So this layer is actually chock full of fossils. And your handout is a pretty good resource for you guys to gaze upon of different types of fossils that we have found here. If you spend some time and dig in here and mine out, you can get some nice slabs of these beautiful fossils that were important in the coal swamps during the Pennsylvanian period. Now, the last thing to talk about for that layer is that orange color. That orange color is not an original part of the rock. What actually happens is, as the rocks are exposed at the surface, they weather. Cracks within the rock act as avenues for fluids, and as they get near the surface, any iron within the rocks oxidizes, forming limonite or hematite. Rust, basically. So as the rocks come to the surface, they get those coatings. As the fluids, come to the surface, they coat the rocks with something that was not original to the rock. Now we want to make a note of that, but we're not going to make that part of our main description. That comes last. So what I want you guys to write down for layer 1 is basically this. Layer 1. Medium gray, silty clay shale. Medium gray, silty clay shale. That takes into account the color. The silty clay shale tells us the grain size and that there's a little bit of silt in a clayey shale. Mainly clay, but a little bit of silt. The word carbonaceous should come next. Carbonaceous. C-A-R-B-O-N-A-C-E-O-U-S. That means that the rock has carbon-rich fossils in them. That word is different from carbonate. Carbonate means that there are carbonate things in it, that they're like limestone. In this case, what you should write is medium gray, silty clay shale, comma, carbonaceous. Remember, carbonaceous means that it has carbonized fossils. Oh, then the word fossiliferous. F-O-S-S-I-L-I-F-E-R-O-U-S. That means there's fossils in it. What kind of fossils? Carbonized plant fossils. So far you should have written down medium gray, silty clay shale, carbonaceous, fossiliferous with carbonized plant fossils. And then below that you could say, since you have the resources, why don't you just pick 3 from your field trip guide? If you guys were actually here, we would say, well, I want you to find one of each of these or 3 of these different fossils and write down their genus names. You guys should know how to do that. You can see that they're italicized or underlined on your handout. So pick 3 of those names and pretend that you found them. I would say we definitely found a Neuropterus. I can see that we found some Calamites and maybe some Sphenophyllum, just in my couple of minutes digging here in that outcrop. Okay? At the end of my description, I will write that the fossils are black, carbonized, period. And then I will write, sort of after everything, there are limonite coatings on the surfaces of fractures and the surfaces of the shale. Keep in mind that last thing I wrote came after the sediments were deposited. It's an alteration product. Now, some people on our field trips have even found a rock called gypsum in little tiny crystals associated with that limonite, but that came last, so don't write that down in your notes. All right, that was layer 1. Let's go down to layer 2. Just a few layers to go. Layer 2 is this. And if you were here, you would say, hey, let's have a campfire. Look, I can break it with my bare hands. It's not a very strong rock. In fact, you might be able to even recognize it from where you are. It snaps. It has real smooth, bright colored coatings on it. And even if it was dry, it would be shiny black stuff. As you guys have guessed, this is bituminous coal. I'm holding this piece because you can actually see this pattern right here is a piece of a compressed log, that you can actually see the impression of a stick or a branch. So it's made of tree fossils, of course. Tree fossils not similar to today's types of trees, but the types of trees that made the coal swamps during the Pennsylvanian. So this is the Ames coal. It's actually a bituminous coal. So what you want to write down is, first in your notes under layer 2, write down black bituminous coal. We've already got the thickness. If we didn't have the thickness measured in there for you guys, you'd have to write that down, but we've already done that for you. The last thing I would say is you might have noticed that the pieces I held up also have those limonite coatings on them. So I would say go ahead and write that down as the very last thing. But maybe after you've written down black bituminous coal with plant fossils apparent in the coal, period, and then write down also has some limonite coatings at the very end. All right, so that's layer 1 and layer 2. Hey, we're almost all the way there, guys. We've only got 10 more layers to go. Layer 3. Oh, don't laugh at that. I got some little pieces of layer 3. It's hard to see. In the outcrop, layer 1 was down here. Layer 2, can you see me tapping away? There's that piece of coal right there. Layer 3 is above this, but it's sort of recessed in there, and I have to pound on it to get a few little pieces out. And those little pieces are dark gray. And if I break it apart, it breaks up into little pieces of shale with some hard parts in it. And if I did break pieces out, I'll show you back when we're in lab, but I'm not getting any fossils right now, but there are fossils in this gray shale, and they are shells. They're shells that are similar to the ones in your handout on the second page, if I can find that second page. There are brachiopods, there are crinoid pieces, bryozoans. We've even found snails. There are some pictures of bryozoans. Just about everything that's on this picture, including corals, crinoid columnals, and so forth, you can find within these dark shales. Now, what I want you guys to write down for this layer is layer number 3. There's just a little tiny thin spot, dark gray, silty shale. And in this case, we're going to write the word calcareous. Yes, there's a little bit of silt in this rock, but it's also slightly cemented with calcite, which makes it have those little hard parts. And of course, that helps to cement some of the fossils together too. But it's not a full limestone. It's mainly a silt shale with a little bit of limestone in it. So it's dark gray, silty shale, calcareous with marine fossils. And then you would say which marine fossils. So the ones I just mentioned. Now the next layer up, that was all we had to do for layer 3. Layer 4 is easier for you guys to see. If you look on the outcrop, ping, 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 is this really hard layer. And that is the Ames Limestone. There's a nice chunk of it that had fallen down, not on my toe. All right, I'm going to do some of the talking from back here in the lab again, although we do have a little bit more video of the outcrop itself. But some of the things are hard to see on the outcrop, so little by little I'm going to work my way up. We've been talking about the Ames Limestone, remember? And the Ames Limestone is this fossiliferous limestone. It's roughly light gray on the outcrop, and in these samples we've got samples of each formation up above. And let me remind you of where we are on your measured section. On the zoomed in on measured section B, this is layer number 4. And it's a tough rock, like you could see me pounding on the outcrop. It goes ping, ping, ping with the hammer. And you can see these big blobby things in there. Those are actually large spiny brachiopods. On some of the samples you can actually see the spines coming out. And In between all of that, all this gray matter is basically broken up fossils like bryozoans, like crinoids, snails, and all of the other things that are present on the diagram that's in your lab, the key that has a bunch of fossils. Now again, what I want you to describe this as is a light gray fossiliferous limestone. It's the Ames Limestone of the Conemaugh group. It contains large brachiopods, small brachiopods, crinoids, snails, corals, bryozoans, and many other types of organisms. So I think you want to make sure that you get all that information down. It's got so many crinoids, in fact, when I look at a broken piece, like right here, if we can zoom in on that just a little bit, you can see how it sparkles. Crinoids just happen to have single unit crystal shells, and when you break them, it kind of looks like marble sometimes. So you may or may not be able to see it in this piece that I have in my hands. But what I do want to talk about is the fact that suddenly in our outcrop in layer 4, we have nothing but calcite, nothing but limestone being deposited. That's important because what that means is any source of clastic sediment, mainly shale and mud and sand, must have been far away. Now keep in mind, like I mentioned to you before, we were on a coastal plain that was very near sea level. It was very flat. So any rise in sea level could have pushed shoreline far inland. And at the time that the Ames limestone member was deposited, shoreline must have been so far towards the mountain range, which would be to the south and east of us, that there would have been no clastic sediment brought out to this area. So the only sediment deposited was the pure limestone of the shells. Now, critters that make limestone hate cloudy water. They hate to have mud in the system. So this tells us that although the sea level was the highest at this time, it wasn't deep enough that the organisms couldn't live. And keep in mind, a lot of organisms that make limestone need to be in the well-lit waters too, because some of them photosynthesize. So we were in warm, shallow, tropical marine seawater that was probably the highest sea level of our cycle of sea level change, but not deep enough that the carbonate-making organisms couldn't thrive. So how long were they thriving? Well, this is about a foot thick. They were thriving for about as long as it takes to deposit about a foot of limestone. How does that compare to these many, many feet of shales and sandstones that are above? Well, that should be a very good lesson to you guys that we can't just simply measure the thickness of the rock and to relate that directly to time. We don't know exactly how long. And we're going to talk about that a little bit later when I summarize the transgressions and regressions. So the other thing I want to talk about with the limestones is the fact that the Ames limestone member is a very good marker bed. So during the sea level rise, it was spread and deposited throughout the area, and oil drillers within the Appalachian Basin will use the Ames limestone in their drilling and mark it. They know exactly when and where, or when it was deposited, at least as a stratigraphic marker. So the critters that made the Ames limestone do not like to have mud in the system. So that's bed number 4. Let's move up to layer number 5. Now layer number 5, I'm going to cheat a little bit because layer number 5 is actually the same rock type as layer number 3. And what you might see, if I can zoom in on some of these things, is when you look at it very closely, there are actually some fossils of brachiopods all over this rock. There's one right there, if you can see where my finger is. I'm pointing to a brachiopod with my right hand. Now, again, this is that dark gray silty shale that is calcareous. Remember, it's different from what we said before, carbonaceous. It is calcareous. But it's mainly shale with some fossils in it. What fossils? Well, the same ones that are on your chart. Not too different from the ones that we saw in the Ames limestone, but these ones include more of those little tiny small brachiopods that are typical of more muddy environments. But don't write that in your notes just yet. Just make sure you write down dark gray, silty shale, calcareous. Contains calcite fossils, including brachiopods, snails, crinoids, and anything else that you'd like to pick from that diagram that we've included in your lab material, because those are just about all present, bryozoans, corals, and so forth. And again, that's in the layer just on top of the limestone. What happened? Why are we suddenly getting more shale and fewer fossils? And the reason is probably either sea level did start to go down. Thus, we had a regression going on, bringing sediments farther out to sea, or not out to sea, but bringing the shoreline farther towards this area, so that we suddenly had a supply of mud. The critters that make limestone don't like mud, so they started to suffer. Now, the other alternative is simply that the supply of sediment started to fill in the basin so that we aggraded up to sea level. Is that the case here? Well, I think maybe there was probably a bit of both. But the change in thickness in this area is not really enough to say, well, yes, it must have been all aggradation. So there was probably some sea level fall and some progradation of a delta that got mud out to this area and started to have a detrimental effect on the fossil life, on the organisms that were living in the ocean, that later became the fossils. I should be careful of how I say that. Nonetheless, make bed number 5 and bed number 3 the same. Now, what's going on with sea level? So we're going back down again as far as the depth of the water. Now, layer 6 is a continuation of becoming more shaly. In fact, we haven't found any fossils within layer 6. And in this layer, if I take it and I rub it on my teeth a little bit, it's very smooth, almost no silt in there. This is a dark gray claystone. Not a silty claystone, but a claystone. And it doesn't contain fossils. We haven't found many trace fossils in it either. But what does that indicate? That indicates probably that the deltaic environment continued to come into this area and stifled the deposition of carbonate sediments. So we don't have any more fossils in this, and it was maybe a nice layer of really muddy water at the bottom of the ocean that nothing could really live in for a while. So that's layer 6, a dark gray clayey shale. Now, as we move upward, we're going to move into layer 7. Now, in my diagram that I have, I want you to notice that I have the line going in and out and in and out and in and out. And that's because it's not solely just one rock type. It's actually interbedded or transitions from slightly coarser or slightly finer material. And the way I've drawn it on your diagram, I've tried to show that it has a number of what we call coarsening upward cycles. And those coarsening upward cycles go from clayey siltstone to silty, fine-grained silty sandstone. Or I should just say sandy siltstone. But it's not really a good sandstone. There might be some small caps of the tops of these little cycles that is a little more sandy. But your description should say light gray clayey siltstone interbedded with light gray sandy siltstone. So you also want to mention that there are several coarsening upward intervals within the entire bed, and that the entire bed coarsens up from bottom to the top, so that there's more of the clayey siltstone at the bottom. It's sort of a transition from bed 6. Up to the top, there is more sandy siltstone, so just slightly coarser. And each one of those little coarsening upward sequences within layer 7 gets entirely coarser on the way to the top of layer 7. Okay? Now, as far as other types of features that we see in here, again, we do see that coarsening upward pattern, but we do not find any body fossils. We have found trace fossils that are potentially marine organisms. Although with trace fossils, you can't always tell whether it's a marine or a freshwater organism. So that is layer 7. Well, one more thing I want to say about layer 7. Remember, we We generally talk about the main depositional features first when we're making the description, and the last thing that we put on is any diagenetic alteration that might have happened after deposition. And in this case, if you look at this little round rock that I have, this is called a concretion. And at some point after deposition, some concretions formed within the layers and make these hard little rocks that weather out on the slope. Now sometimes in special deposits, if you bust open a concretion, it might have a fossil in it. In this case, they do not. We have not found any fossils inside the concretions, but that's something that you can add to the end of your description of layer number 7. All right, let's move on up to layer number 8. Again, on the outcrop, layer number 8 is above where we're actually standing on the outcrop, so it's sort of covered by weeds. There might be a couple little shots that we could slip in there that you might be able to see. But the base of layer 8 that we would actually be able to get to is slightly more sandy than layer number 7. So in the larger cross-section, in the larger scale cross-section, layer 8 is this big thick interval, and again you can see all of these coarsening upward sequences, and the sizes of the particles go from the bottom. They're mainly siltstones with fine-grained sandstone caps, or fine-grained sandy siltstone caps, and then as we go up higher and higher, these beds that are more coarse, that include fine sandstones, get thicker and thicker, and the entire section also coarsens up. So what I want you guys to write for layer 8 is medium gray siltstone alternating with light greenish gray fine-grained sandstone in coarsening upward cycles that throughout the entire layer 8 coarsen from mostly siltstone at the bottom to mostly siltstone and fine-grained sandstone at the top. Now, one thing that I want to mention to you guys about this layer is that coarsening upward probably means that we were getting towards shallower water, and the entire coarsening upward package indicates that we had the progradation of deltaic facies, probably still in the marine environment. But we're going to refer to this environment as deltaic. Now the coarser material near the top and the coarser material at the top of each one of the smaller cycles either indicates that we were at a higher position on the delta and maybe sea level was bobbling up and down, but it could also mean that from time to time big storms were hauling across the area, and the storm waves could get deep enough to interact with the sediment-water interface, stir up the sediments, and wash out some of the fines, thus making those nice layers of sandstone, the fine-grained sandstone. And so we get those intermittent layers of sandstone that may actually be what we refer to as hummocky cross stratification. Now, we referred to that earlier when we were talking about sedimentary structures. But for the most part now, the main thing you want to notice is that you have those coarsening upward cycles, and some of the coarser sand intervals might actually be hummocky cross stratified. And again, that's in layer 8 in a part that we can only really see up on the outcrop and in your complete section diagram A, that's the zoomed out measured section. Now, what happened after that? We're not going to climb up to the very tippy top, and in fact we're going to cheat. We're going to tell you guys that for layer 9, 10, and 11, we're going to make those rock types the same as layers 4, 7, and 8. And you can see on the diagram, they look pretty similar to those. So what happened? Well, when you see layer 9, you can see that that's a limestone again. Now, we referred to the lower limestone as the Ames Limestone, remember. This upper limestone is called the Skelly Limestone. Now, I have not actually been up there to see it myself, but my student who did his capstone out there collected samples of it, and for sure, it's another marine limestone. What happened to sea level? Well, we had sea level gradually going down and the delta prograding out into our area, and then all of a sudden, bang, limestone again. That means that we had another sea level rise that pushed shoreline farther to the south and east of us towards the mountain range and made it nice and clean, fresh, or not fresh water, but nice marine salt water that was still shallow enough for organisms to make a lot of limestone. So we sort of reset the button. We didn't quite make it up to land, but we hit the reset and we started another cycle. So we had layer 9, 10, and 11 where we have the marine limestone and then the deltaic sequences that are slowly coarsening upward. Now the difference here is for layer 12 is a different rock that's on top. In layer 12, I've got a chunk of it right here. And there are chunks of this laying at the bottom of the outcrop that we had to stumble over to get to. And it's a nice cap of sandstone that's actually the rugged sandstone that's forming the cap rock for the hill right where we're at. And it's a medium-grained, light greenish-gray sandstone. So your description is going to start like this. Light greenish-gray, medium-grained wax stone. It's kind of a dirty sandstone. It contains cross-bedding. That's interesting. We haven't really mentioned cross-bedding yet, but when we talk about cross-bedding, we generally indicate that there's some sort of one-directional current, like in a river. So in our section here, we go from the marine limestone, the delta progrades through, and then it gets shallow enough that we actually come up above sea level and deposit a river environment. So that's a whole cycle. Okay, so on the top of this, we can also see some burrows on layer number 12. All right, so in summary, we have 12 layers. They include fossils in some of the layers. The different layers include different environments. And we have layers that are kind of in a sequence that show patterns that we're going to talk about in our next installment when we go back into our lab and have that discussion. Just to remind you of where we are and where we went, here's the geological map again. So we started here in Marietta right on the Ohio River, and then we traveled upriver about 15 to 20 miles and went to an area where there was an outcrop of the Conemaugh group, which is the lighter turquoise colored color on this map. That's the northernmost end of something called the Burning Springs Anticline that extends down here into West Virginia. And you can see some of the structural contours that are drawn on this map from either right now or from before when we were zoomed into it a little bit more. We got out and we climbed up the outcrop right here where there's a little A that actually stands for the outcrop of the Ames Limestone. And we described some of the sediments that we saw for you. And I also tried to put you into an understanding of the larger perspective as far as where this continent was paleogeographically, that we were adjacent to the Appalachian Mountains that are mostly eroded away now, and what we see today are the erosional remnants of just the foothills of the Appalachian Mountains. And what we sort of want to do now is we want to get an understanding of what the environments of deposition were. So we're going to start to walk into a little bit of the interpretation, and then from the environments of deposition try to understand some of the changes that were going on with sea level. So we have a number of different resources that you should have printed up or should have available to you. And the main thing I want to talk about right now are the environments on the two cross sections that you have at the end of your lab. The first one I want you to refer to is cross section B. Let me move the camera so that I can zoom into that one and we can see it very clearly. Hopefully things are lined up right now. I need to adjust a couple things here. Zoom in. I guess that's as good as it's going to get right there. A little crooked. Let me see if I can straighten that out. Well, that'll have to do for now. Anyways, what I want you to do on this cross-section, please note that it is cross-section B, and you should have notes in here for each of the individual layers. And again, I'm going to review those fairly quickly because I have some of those samples on the table right behind me right now. But environmental deposition, you guys can take pretty good guesses. Just write these down in the environment space at the end for the time being. Layer 1, of course, was shale with a lot of carbonaceous material, a bunch of plant fossils in them. So we could probably say the floodplain environment or a swamp. And of course, layer 2 being coal was a swamp environment itself. Layer 3, I'm putting in the word marine. Layer 3, 4, and 5. Each of those layers are probably occurring after there was a transgression and we had marine conditions, And that's, again, based on the shelly fossils that we see. Progressively up from that, layer 6, 7, and 8, I've written the word delta in there. And that's going to come in handy in a minute or two. But for now, just write the word delta. Keep in mind that it's most likely a marine delta, although we haven't found a lot of body fossils of marine fossils within those sediments. So that's what I want you to think of for right now for cross-section B. And now, pay close attention. I'm going to flip that over because mine is printed on two sides, and I want us to finish the things that are for layer or for the cross-section A. Let me make sure that I'm lined up appropriately so you can see everything in there. Good. So here's what I want you guys to write as far as the environmental interpretation on this side. Remember layers 9, 10, 11, and 12. We didn't actually go and see, but I did tell you that they are similar to some of the layers below. Now, as you see up in the instruction part, I wrote, we're going to do an interpretation of the environment, but this is going to be a little different from the other side. We're going to just try to determine whether it's land, delta, or marine. And the reasons I want you to use those letters L, D, and M is because I don't want you to confuse it when we're using the letters T and R for the transgression and regression. So starting from the bottom, of course, the first 1, 2, 3 layers, well, the first 2 layers, I'm sorry, should be L for land. Those are deposited on the surface of the continent above sea level. Layers 3 and 4 and 5 put an M because those have marine fossils. Layers 6 and 7 and 8, you're going to put a big D in there for delta. Now, once we get up to the top of layer 8, suddenly there are limestones again, and that's marine. So something happened there. By the time we got up to the top of layer 8, there may have been another transgression. Oh, wait, I'm jumping ahead of myself. But anyways, there must be a reason why it cleaned up and we suddenly got more marine limestones deposited there. And then on top of that, we have the layer 10 and 11, which are basically like layer 7 and 8, I believe. And for that, we're going to put a D again. And then on the very tippy top, we have some sediments that we think are probably river sandstones. So we're going to put an L for land. Now, if you refer to the very last column, I want you to write either T or R. And the only place that you're going to put the T for transgression are in these areas that are right next to those limestones. Everything else is going to be in the regressive part of the sequences. A sequence, or what we're going to call a cyclothem in a minute, is a cycle of sea level rise and then sea level fall. So what we actually see here are several episodes of sea level rise and fall. So this sort of helps us see that on the larger scale of this whole diagram, there are several cycles of deposition going on here, and they're probably controlled by sea level rises and falls. So transgression versus regression. So in the lowermost part of this cross-section A in the right column, you're going to put an R for regression because the sea had regressed away so that the only thing deposited in there are terrestrial sediments. Again, I've got to be careful about using the word terrestrial because we're using the letter T for transgression, not terrestrial. But here, put the letter R. As you come up into the layers that are basically layer 3, 4, and 5, you're going to put a T there because something had to happen in order for the marine sediments to be deposited in there. And actually, for what I've got it in here, it is, I think, layers 3, 4, and 5. You put a T in there for a transgression. So the sea had to come up. The sea had to flood the land in order to make those limestones that are there. Now, after the deposition of bed number 4, 5, 6, 7, and 8 must be regressive because the sea level is starting to get shallower. Maybe the sea level actually did go down, but also what was probably happening was deltaic sediments were prograding from the shoreline and filling the available space for deposition up to sea level. But after the deposition of layer 8, suddenly sea level must have risen again. So in that area is where we're going to put our T for transgression, and then all of the rest of the layers are going to have R for regression. And in this case, for our cycle up at the very top, we went from marine to delta all the way to land. Even though we didn't have any terrestrial sediments, any river or floodplain or marsh sediments, swamp sediments at the very top of this cycle, we still had the end of a cycle and the beginning of a new one right there where we had that transgression. But at the very tippy top, yes, we get to terrestrial sediments like sandstone. So in essence, what we have here are at least 2, and more than 2, full cycles of sea level rise and fall. Right down here at the bottom, we see the end of one. This is the regressive part of one of those cycles, and that's the end of a cycle that probably started below someplace. And then we have right here where this transgression starts, that's where we'll start them, another sequence starting where we have a transgression and then a regression all the way up to here. So that's a second cycle. So here's a cycle going from here down to there, and there's a cycle down here. And then here's a cycle up here where we have the transgression and then the regression. Like that. So what we have here are 2.5 cycles. And there's a special word for that type of cycle that we use for Pennsylvanian cycles that actually contain coal, and that is the word cyclothem. Dun, 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 dun. I actually have, part of the C got erased there. That's how it's spelled, Cyclothem. That is a transgressive regressive cycle that's characteristic of Pennsylvanian age cycles that commonly have resources in them like coal and limestone. And during the Pennsylvanian period, we may have had as many as 14 to maybe more than 24 different cyclothems happen, where those are sea level rises and falls, depending on how the worker that's working on them counts them at the time. And so what we're seeing is actually 2.5 of the Pennsylvanian cyclothems. We'll learn about them in class very soon, but we can correlate these all over the sort of eastern Midwest around Pennsylvania, West Virginia, and Ohio, and we can actually correlate these same sea level rises and falls if we go farther out west into Kansas, Oklahoma, Texas. Those cyclothems are the same beats of sea level rises and falls that were recorded in the sediments that were caused by, you got it, glaciation of Gondwana as Gondwana sat on the South Pole during this time. So many times the glaciers built up, sea level went down at that point, and then the glaciers melted, which raised sea level, and that caused our transgressive regressive cycles that we're referring to as cyclothems. Now, a question might be, does this succession reflect Walther's law? And you're darn right it does. Because as you go up these cycles, you can imagine that especially in some of these top cycles, that if you started in the marine environment and then walked up the delta, you would progressively go through environments of coarser and coarser sediments. And then maybe if you were in the top cycle, you would go up through those coarser and coarser sediments and then might even walk up onto land and be in a river's floodplain or in a river channel. So yes, Walther's law is honored here in many cases. There are a couple of little unconformable spots there, but for the most part the sequence is fairly conformable. The time breaks would have been pretty minimal. Another thing that we want to think about is progradation. Keep in mind I made a big point of the fact that with these layers, especially layer 5, 6, 7, and 8, all coarsen upward from that limestone. From the limestone that's layer 4, going upward you get more and more shale, and then eventually it gets more coarse from just a clay stone all the way up to the point in which the sediments are much coarser and include sandstones. So progradation is shown in this area because we get progressively coarser and coarser sediments. There are also smaller cycles within the larger cycle which indicate pulses of perhaps sea level rises and falls and or intermittent exposure of the sediments to storm waves. So that could have happened as well. But we see several layers, several levels of cyclicity here on the smaller level with these small coarsening upward cycles, and then in the overall larger coarsening upward of the deltaic progradation that we can see just in this one spot. So that's one of the things that's kind of cool about this one spot, because we can just go a few miles away from campus here and see two, count them two, if not three, cyclothems exposed in an outcrop, and we can try to see the fossils. We can even collect very cool fossils that you guys could sell for big bucks on eBay or something like that. Now, the one last thing I want to remind you guys of is the fact that this area is sort of historically important as well, and when we go back to the main map and we look at the area that we're talking about, again, this is the northern nose of the Burning Springs Anticline. It actually goes much farther south into West Virginia, and it was formed within Pennsylvanian and Permian sediments, but it was formed at the tail end by deformation at the tail end of the Alleghanian orogeny. The Alleghanian orogeny impacted the Appalachian mobile belt and buckled up and folded rocks all the way here practically to Marietta, Ohio. This is one of the westernmost folds of that structure, of that orogeny. Now, it's kind of historically important because that area was one of the very first giant oil and gas fields, because anticlines help trap oil and gas in it, and one of the first ones ever taken, probably the first one ever taken in an armed conflict during the American Civil War. I think in your notes I might have put this might have been one of the very first places that oil and gas was drilled for economically, specifically looking for oil and gas back in the 1850s and 60s, and that might be a little conjectural because there are some other places that might try to claim that as well. But it is the first place that a professor, a scientist, actually described the trapping mechanism of an anticline with oil and gas. And that guy's name was good old Ebenezer Andrews, who was a geologist here at Marietta College during the 1860s. And Andrews Hall is actually named after his brother, who was the president of the college. So Israel Ward Andrews was Ebenezer Andrews' brother, and that's who the Andrews Building is named after. Now, if we want to look back at some of the rocks that we had the pleasure of looking at yesterday, I can move our camera over here and briefly go through the layers one more time. And I can show you some samples that we have collected over the years that are present in our collections, such as layer 1. And here we can definitely see some beautiful fossils that are present in this. Oh, no, I guess we can't until it focuses. Yeah, all those little black bits are pieces of plants, and we can see them on the tops and bottoms, little fern leaves like right there, beautiful impressions, and also carbonized pieces. So there's a piece of that shale that's not in the wild, that's easier to see because we're not having to stand on the muddy slope. Here are a few more pieces of that. Let me see if I can get it to focus. You see those little stripy lines? That's the same plant that you guys learned as an internal mold. That's one of those Calamites scouring rushes. Layer 2, of course, is the coal, and I do have a tray of the coal. I'm not going to spend much more time talking about the coal. And layer 3 and layer 5 are the same layer. And what I'm going to show you here is on some of these chunks that we've got in this tray. I think I might be able to pick them up and point out to you some of the fossils that are on here. They're not jumping out at me right now, but I can see some little fossils. Let me see if I can get that to focus. Those are little brachiopods, and there are snails and so forth in those. This is that layer number 3, that's the calcareous shale. It's kind of hard indurated because it's cemented with limestone, and you can see some of the brachiopods right in there. But it's definitely marine, so we have a change in environment. The next layer up, of course, is layer 4, that has that's basically the Ames Limestone. And on this piece you can see some big brachiopods that are present. Let me make sure that it's focusing on those things. Focus, there we go. And then there's some other pieces. There's a big brachiopod, but this whole chunk of limestone is made of basically nothing but fossils, crinoids, bryozoans, brachiopods, and so forth. Layer 5, I believe the Ames Limestone is layer 4. Layer 5 is, again, like layer 3, made of a shale that contains a lot of fossils. And here are some of the examples of those fossils, again, that have brachiopods. They look about the same. Layers 3 and 5 look about the same. And we cheated by just telling you, hey, just use the same description twice. Here are some nice pieces of layer 6, which is boring because it's just this really monotonous claystone that doesn't have hardly anything in it. And let me see if I can get it to focus on that. And when I chew on it, of course, it becomes very clayey and doesn't have hardly any silt. And then progressively as we go up through the layers, layer 7 is a little more silty. There's not much I'm going to show you. Of course, one thing I did forget to mention was that there are these little structures called concretions within the limestone, within the sandstone and shale. So write down the word concretion, C-O-N-C-R-E-T-I-O-N, for being in there. Also, as we go up to the next layer, I believe this is layer 8 now. Layer 8 contains more coarse silts and some honest-to-goodness layers of fine sandstone like this lovely piece. And you're not going to be able to see much in the camera there, but that is a piece of that sandstone. But keep in mind it's more well cemented because the sandstone is more porous, and through time it got cemented up better than the shales below it. At the very tippy top, keep in mind that layers 9, 10, and 11 are basically repeats of layers 4, 7, and 8. 6 might be in there, but I just haven't dug it up yet. But anyways, 9, 10, and 11 are the same as 4, 7, and 8. And then at the very tippy top, layer 12 is this medium-grained, light greenish-gray sandstone that's basically a river channel. It's got cross-bedding in it. You might not be able to see it from your pieces, but it does have some burrows in it. Those burrows are probably from freshwater organisms. Anyways, I'm hoping that you have enough information now to finish your questions that you have to answer for this lab. So just before I sign off, let's look quickly at your question sheet, because this is one of the things that you want to finish off, as well as your cross sections to mail back to Frank so that we can say that yes, you have done the lab. And so this last page, there are a number of questions. What's the rock unit name of the lower fossiliferous limestone? Hopefully we've answered that question. That should be on that stratigraphic column that is with the Paleo Geography. What's the rock unit name of the upper fossiliferous limestone? That should also be included there, and we've mentioned that. Name 3 animal fossils, name 3 plant fossils. So take your material from your lab. By the position, and answer those questions just by picking some random names from, not too random, because make sure they're the right environment. Make sure the plants are in the plant column and the animals are in the animal slot. But go ahead and just choose any of the 3. Since you guys couldn't go out there, you can just take our word for it. The second number 4, I don't know why there are 2 number 4s. I need to change the numbering on that apparently. By the position of the coal layer relative to the fossiliferous limestone, what happened to sea level? I think you can do that. Number 5 is just saying write down the descriptions of all the different sediment that we look at. In the environment depth column, we just did that, right? L, D, or M. In the zoomed out stratigraphic section, write T or R, and I did that with you guys. Are the transgressions or regression intervals of equal thickness? And the answer to that is no. In fact, that's kind of a weird thing for you to think about, but it might actually make sense, because when there's a transgression, you're basically pushing the source of sediments so far away that you don't actually deposit many sediments in the area far off the shelf during the transgression, and it's during the regression that you actually fill that space that was created by the sea level rise. So even though time, they might represent the same amount of time, oh, I don't even know that. But you can't tell time just by looking at the thickness. So the limestone may include the same amount of time as all the sediments deposited in the shales, or it may not. But keep in mind that you don't know that. On question 9, okay, question 8 has a little bit about progradation. Hopefully I've explained enough of that. 9, what is the term for cycles of alternating marine and terrestrial sediments? And don't forget the word cyclothem. I just like saying that. Does it reflect, okay, layers 8 and 11 are coarsening upward beds from mudstone to sandstone. What do we call this when the sediments grow basinward? So hint, hint, it might be progradation. Does the succession reflect Walther's law? I'll let you answer that. Which sediment rock types are deposited during sea level high stands? The answer I want you to put for that is, when the sea level is the highest, you get mainly limestone and shales. Now, if the water were very deep, it would be too deep to make limestone, but in these shallow basins, the sea level being high meant that the shoreline was pushed farthest away, so the clear tropical water, even though it was a little deeper than near the shoreline, there was no mud coming out, so the critters were happy. So the sea level high stands were basically limestone and shales. What type of structural deformation is responsible for the old Oconoma group rocks being exposed at this location? An anticline. I think that's what we want there. What type of tectonic stress? Compressional. And then you can read that a little bit. The only thing I might say here is that I'm not sure if it's true that this is the oldest area where oil and gas were drilled. People in Pennsylvania might be kind of miffed if they had to argue about whether or not it was actually near Titusville or whatever that is. And you can find some of the answers to this last bit in your textbook or during lecture coming up soon after your test. So thank you for our field trip. If you guys have any questions about how to answer some of these questions or how to fill in your lab, please contact Frank or Dave, and we will be sure to get back to you and make sure you get the correct answers for you to submit that to us.